and welcome to today's webcast. What you see on the screen here is an outline. Sorry about that, I'm just gonna update my screen. Okay, so the outline for today is a quick introduction by me, the host. My name is Kasper Pihl Rasmussen. I'm an application engineer here at Anybody Technology. Following that, we will have the presentation from Anand Gopalakrishnan, who is an application engineer here at Anybody also. So today's presentation will be about man-machine simulations, challenges and solutions, and also a bit of theoretical basis of the system. Anand will then follow this by a live demo where he will show some of this stuff off. After that, we will have some final words again, and we will end it all with a Q&A session. For those of you who are new to the webcast system, please familiarize yourself with the control panel. As you can see, you can expand and collapse it by using the red button. And then you can, at all time during the webcast, you can use the question panel to ask a question. The questions will be answered either using the chat directly, or they will be answered in the Q&A. And if we, in the interest of time, cannot make it all, we will surely answer you by email. If you're also new to the Anybody modeling system, it is a software for performing simulations of the musculoskeletal system for analyzing the human body biomechanically. The software also has a repository, which is a library of models. More specifically, the AMMR includes specific parts of the human body from different published studies, which is then put together into a full body musculoskeletal model. Furthermore, it also includes of different applications of, for example, activities of daily living and other ready-to-use scenarios that can be used as templates. The entire AMMR is also regularly updated by the people here at Anybody Technology. And we see a wide range of simulations options, which include motion capture to define movements, ground reaction force predictions, algorithms, imaging for patient-specific anatomical scaling, and man-machine simulations, which is the topic of today. We see a wide range of application area for the software. In principle, it's human-based optimization. These themes you can see here are the most commonly encountered research areas. So the three main components of the modeling system, I'll quickly go over these because most of this will be explained more in depth by Anand. But the first component is the body model, which I just mentioned before. And then the input is the motion and the forces. And then there's the environment, which can be stuff like exoskeletons, but it's motion or motion constraints. All these things then go into a single human environment model where you can do inverse simulations, and you will get out the muscle forces and the joint muscle reactions. And this is an example of such a simulation. If this isn't your end goal, you can also do post-processing. For example, doing getting data for your finite element analysis. And lastly, you can do these iterative design optimization studies where you use the information for optimizing your environment. So this was a quick rundown of the software, and I'll now give the word to our presenter today, Anand.
Thank you for that introduction, Casper. So we will now get started with this webcast by first looking at the outline of what we will be going over. So we'll start with a quick introduction to the term man-machine systems and also motivate the reasons for why we would like to simulate them. We'll then look at the theory underlying these simulations and highlight the conceptual challenges that stand in the way of implementing these theories or this theory in practice. We'll then talk about overcoming these challenges and how certain tools and algorithms within anybody can help us in this process. And we'll finally see how all these concepts come together by solving a live man-machine problem. And we expect that this demo will put a lot of things in perspective that we will talk about now. So what are man-machine systems? For this, let us turn towards Newton's second law, which states that any kind of free movement of the human body would require some sort of interaction between the human and its environment. So for example, this astronaut in space would necessarily have to push off against the manipulator arm, which is holding him or her up, if they were to reorient or move around in space. So in this case, you could consider the environment to be the manipulator arm, but then it could also include any foreign objects that were mounted on the human, such as the spacesuit. So basically, the definition of the environment and your human and where the boundaries meet is something that is sort of left up to you. But for the sake of this presentation, let us just say that anything that is apart from the actual biological human is what we will refer to as the environment. And in fact, just to clarify the term itself, let's just say that all these non-human entities can be lumped under the term machine. And this is the terminology that we will follow here on. So if we talk about the design of machines, if your machine was an exoskeleton, then a very reasonable question to ask would be, how much external support does this machine provide? If your machine was an implant, then a good question would be, what is the load that you need to design this machine for? And if it was a cycle, then it could simply be, what is the best design for optimal performance? Now, what is common to all these questions is that they require some knowledge of the effect which the machine's design has on human biomechanics. Now, conversely, the machine's design itself can also benefit from certain aspects of human biomechanics. So, for example, the size and the weight of the exoskeleton, which in turn determines how much assistive power it's capable of delivering. Now, this depends on the baseline ability of the user. And for the cycle, its design can actually benefit from the fact that the legs are actually stronger in certain phases of the pedaling cycle. So it is clear that the effect of both the machine on the human as well as that of the human and the machine are both equally important. And this is what we describe as a symbiotic relationship. And this is also the reason why it is best to study man and machine as a single system. Now, since these mutual effects of man and machine can be extremely unintuitive to understand in many cases and also very difficult to measure experimentally, we turn towards computer simulations, so dynamic simulations of man-machine systems, in order to try and understand them better. So what do we stand to gain from man-machine simulations? Most obviously, it helps you study the effect which a machine has on human biomechanics. It helps you evaluate the performance of the machine when it's working along with a human. And this is particularly from the point of view of trying to optimize the design of the machine for human needs. It helps you estimate man-machine interaction forces that could otherwise be very difficult to measure. An example being the rubbing friction due to the straps of an orthotic device. And most importantly, if you're trying to convert your machine to an actual product, it can help you save time and costs on experiments and design prototypes. It can also help you sort of shorten the time that it takes for your product to reach the market. So now, having motivated the reasons for man-machine simulations, let us see the methodology. So there are two sort of ideologies that you could follow when you're trying to build these simulations, them being forward and inverse dynamics. And I would like to point out that for this presentation, we will only be discussing inverse dynamics-based man-machine simulations. So let us try to see how standard inverse dynamics works with the help of this very simple example. It's a three-link mechanism. It's an open chain, which means that it does not loop back onto itself. It consists of three revolute joints, which are driven by motors, which supply a certain level of joint torque or joint moment. Now, inverse dynamics always starts with the assumption that the motion and the external forces acting on the system are known. So you can use the equations of motion to compute the joint moments, which are just the torques being supplied by the three motors. So in this figure, the more red a motor is, the higher the torque it is producing at that given time instant. Now, once you've computed the joint moments, you can go ahead and compute the joint reaction forces and the interaction between the linkage and its environment, which in this case would be the ground. But what if we were to replace these motors with muscles? So it seems quite obvious that the moments that were previously being supplied by the motors now need to be produced by the muscle forces. So if we are trying to compute individual muscle force values, a good approach seems to be to try and decompose those joint moments into individual muscle forces. However, there is an issue because in this system, and as well as in most actual musculoskeletal human, the number of muscles usually exceeds the number of mechanical degrees of freedom by a very high number. So this means that you have infinite possibilities when it comes to the number of feasible muscle forces because you have all these infinite solutions are equally capable of producing the required joint moments. So the solution is to resolve these infinite possibilities optimization. And such an optimization has a hypothesis that the muscles are recruited in the most optimal fashion possible in order to try and produce those joint moments. And this notion of optimality can be introduced using a cost function such as, for example, the minimization of muscle activation cubed. So once you've computed the muscle forces, as a next stage, you can compute the joint reaction and the linkage machine forces. So this is how open chain musculoskeletal models can work, where your limbs are your links connected by mechanical joints and your muscles following piecewise linear paths. So, but what happens now when you switch over to closed chain systems? So over here, we've converted the three-link mechanism into a four-link mechanism by closing the chain, and now the system just has 1 degree of freedom. So if we were to start with by measuring the motion, we should be able to use the equations of motion to compute the joint moments. However, the issue is that there isn't a unique solution. As you see in both these cases, you have completely different joint moment patterns that are both producing exactly the same motion. So you have infinite possibilities over here before computing the joint moments. And then if you are now trying to replace the motors with muscles, you have a second layer of infinite possibilities between the joint moments and the forces. Now, like a rather brave approach to solve this problem would be to have 2 successive levels of optimization, but this would result in extremely slow simulations. So why are we concerning ourselves with closed loops in the first place? Because inverse dynamics seems to work just fine with open loop systems. The reason is closed chains are all too common in man-machine systems. So you see over here Casper, who is our host today, holding up a chair. And if I were to ask you to just analyze the kinematics of this pose and try and predict what were the interaction forces between Casper and his machine, this seems to be a very reasonable solution, and this would result in a certain set of muscle forces that were perfectly symmetric. But then there is no reason why Casper could have been completely disusing his left arm and trying to compensate with a very strong movement with his right arm. And the thing is, there is no way you can distinguish this just from the kinematics. And so there are infinite possibilities for the moments and the muscle forces in these closed loop systems. And you find closed loop systems even within the human itself. For example, in the shoulder, the foot, and the forearm. So you would have to have the capability of modeling these closed loops accurately if you want a physiologically realistic simulation. So now having sort of had a quick crash course on inverse dynamics, let us try to highlight the challenges that stand in our way. So the first challenge, which is obvious, that standard inverse dynamics fails with closed loops. And these closed loops are unfortunately common when it comes to most man-machine systems. The second challenge is actually creating the man-machine model itself, because creating closed loops can be a huge challenge. For example, if you look at these two man-machine systems at the bottom, you can see that it's a musculoskeletal model that has been inserted into a fairly complex environment. And the nature of the closed loop is also quite tricky in the case of the car, as you see in the bottom left. The third challenge is the control of man-machine interaction forces. To understand this, think of, just imagine that you're trying to run a simulation of someone holding an egg, pinch holding it between 2 fingers, And this case versus the case where someone was pinched holding a metal ball. Now, there isn't a way that standard inverse dynamics can actually sort of distinguish between these two cases and force on the egg so as to ensure that the egg doesn't crack. So, having outlined these challenges, let us now get into solution mode. So, we'll look at how there are certain tools and algorithms in the Anybody modeling system can assist in overcoming. The first challenge was how can we get closed loop inverse dynamics to succeed? And the solution lies in a method known as direct muscle recruitment. So this was what standard inverse dynamics looked like, and this obviously wasn't feasible because we had two layers of infinite possibilities in this workflow. So the solution is to try and reduce this to just a single layer of infinite possibilities. So what we are trying to do is essentially directly compute the forces, the muscle forces, the joint reaction, and the linkage machine forces, or the man-machine forces, directly from the measured motion. The important point is that we have completely eliminated joint moments as the intermediary between the motion and the forces. And this method is known as direct muscle recruitment because you directly go from motion to forces. But we still need to resolve these infinite possibilities somehow and come up with a unique solution. And for that, we turn towards our good old friend optimization. So the hypothesis underlying such an optimization is that the motion, the observed motion, is produced by recruiting muscles in the most optimal fashion possible. Another feature of direct muscle recruitment is that the three forces which form the output are actually computed simultaneously as opposed to one after the other, which you might remember was the case with standard inverse dynamics. So the simulation is capable of capturing the interdependency between these three. And so the simulation is actually capable of exploiting the exact nature of the boundary condition between man and machine and try to reduce the muscle forces to the greatest extent possible. Now let us go back to the problem of Casper trying to hold up the chair, and now let us analyze it through the lens of direct muscle recruitment. So with a cost function such as the minimization of muscle activation queued, and with a completely symmetric musculoskeletal model and a completely symmetric chair model, it seems intuitive how direct muscle recruitment would come up with such a solution, just because the most optimal strategy would also be a symmetric strategy. However, if we were to completely weaken the muscles in the left arm, or if we were to penalize these muscles, the activations in these muscles quite highly in the cost function, then we can see how a completely different set of man-machine interaction forces can be predicted. And this is what we mean by trying to exploit the boundary condition, which in this case was having both hands hold the chair. So direct muscle recruitment is capable of solving both open as well as closed loop systems, and this is why it's the default inverse dynamics algorithm. And it helps you solve rather fairly intricate man-machine systems. The next challenge was the creation of closed-loop systems. And the solution to this lies in a set of tools known as measures and drivers. For understanding measures and drivers, let us first look at how exactly we created these closed loops. We created a closed-loop chain from the three-link mechanism. For this, the first step was to measure this position vector. And the second step was then to try and constrain this vector, the two components of this vector, to 0. The closed chain. Now this is essentially how anybody approaches the problem of creating closed loops. So the first step is achieved by a set of tools known as measures, and the second step is achieved by a set of tools known as drivers. And so you have a set of kinematic measures which can measure a variety of physical dimensions, and you then have a set of drivers which can constrain the values of these measures to certain values, to certain fixed values, or even drive them along certain specified time-varying trajectories or time-based trajectories. So if you were trying to create a complex man-machine model, instead of trying to exactly work out the equation for that kinematic loop, you could simply start with, so let's take the example of connecting the hand to the handle. So you could start with creating a set of measures which measure the relative position and orientation of these two segments, and then use a set of drivers to constrain the values of these measures to certain fixed values. And this will make sure that the hand and handle maintain a fixed relative orientation and translation throughout the course of the simulation, or throughout the course of the movement. So another important feature which we will really see, it helps us a lot in the demo that we will be doing today, is hard and soft drivers. Now a hard driver is a zero compromise driver, which means that its constraints will always be exactly fulfilled, while a soft driver's constraints are only fulfilled. A good example is when you're trying to build a motion capture based model where you're trying to make your model move in a fashion or move in a certain way such that the distance between a set of red markers attached to the model and a set of blue markers, which are your experimental markers, such that these distances are minimized. And that would imply that your model is moving just like your actual human. So you could start this by creating a set of measures between each pair of markers and then using soft drivers to try and drive them to zero. And when you run the kinematic simulation, you get a model that moves like your actual test subject. Now, one advantage of these using hard and soft drivers is you can sort of combine them in clever ways, and you can get what is known as machine-driven motion. Now, machine-driven motion lets you attain complex motions without the use of any mocap. So which means that if, let's say, you had the idea for a certain a design for a certain exercise machine, you could actually just create the model for your machine and use machine-driven motion to animate to see how your human moves in the machine. So you don't really spend time on a prototype or trying to record motion capture data. The next challenge was the control of man-machine reaction forces. And this is done using some special force elements. So if you take a case of where we're trying to simulate double support stance, and this is obviously a closed loop system at the legs and at the hands as well. So let us think about how we create the closed loop at the feet. So we rigidly weld each foot to the ground, done using 6 measures and drivers respectively for each foot. And then you could run direct muscle recruitment with a certain cost function to actually compute the muscle forces and the man-machine reaction forces. However, the issue is that you do not have any control over the man-machine reactions. Let us see what this exactly means. So if I try to focus on the right foot, which you see in this diagram over here, there are 6 degrees of freedom, or 6 that have been constrained. So you'll have a reaction force and a reaction moment between the ground and the foot. Now there is a requirement that the center of pressure corresponding to this loading scenario must lie within the bounds of the foot. But however, if we were to try and convert this force and moment into its equivalent center of pressure, there is absolutely no requirement that the center of pressure actually lies within the bounds of the foot. And the simulation could potentially exploit this to unrealistically minimize the muscle forces. The solution is to try and decouple the constraint's kinematics from its kinetics. So which means that we switch off the default reaction forces which a driver provides to maintain that constraint, and instead we enforce that constraint using special force elements. So if we look at the double support stance example again, for the ground foot constraints, we start adding these special force elements which supply forces in the vertical direction or the y direction, and this force is applied to a certain point on the foot. Now you can add any number of such force elements, and each element also has its own optimal force. So when you run inverse dynamics with direct muscle recruitment, you can now include these the forces in these special force elements in your cost function. So since your net ground reaction force can only be a linear combination of these special force element or these special forces, you automatically ensure that your center of pressure always lies within the bounds of your feet. This is the foundation for the ground reaction force prediction algorithm in any body, which many of you might have already heard of and maybe even tried out. There was a webcast on this a few months back. So ground reaction force consists of 2 components, and so we create 2 sets of special force elements for the normal and friction force. And then we actually couple the 2 sets of force elements such that the frictional force can never exceed mu times the normal force. And this is the foundation for the ground reaction force prediction model. So this ensures that you get reaction forces, and so basically you can bypass the stage of measuring your ground reaction forces, and instead try and get them predicted by your simulation itself. And this can again save you time and probably expenses. And it also helps you in a way. So this automatically ensures that your friction is realistic, and it also makes sure that the center of pressure lies within the foot. So if you guys are interested in the validation of such models and also in just getting to know more about the theory, I would refer you to the webcast by Dr. Michael Skipper Anderson, which you can find on the Anybody YouTube channel. So this wasn't really a challenge, but something that we've been talking about since the start of this presentation is the optimization of the design of machines according to human needs. This can be done using a certain form of optimization. So for example, let us look at this case where we are, say, trying to optimize the design of the cycle. So we're trying to find out the best which minimizes the activation in the quadriceps when the person is cycling at a certain speed. Now this can be formulated as an optimization problem where your cost function is the minimization of quadriceps activation. And you could then parameterize the design of your cycle and then treat these parameters as the unknowns in the optimization. For example, I could parameterize the design of my cycle in terms of these three physical dimensions. And then you run an optimization study wherein you, in each iteration of the study, direct muscle recruitment is rerun for the entire motion, which is probably one pedaling cycle. And then the parameters of the cycle are adjusted iteratively until you've managed to minimize quadriceps activation. If you are interested your machine in a CAD software, you could possibly do that in SolidWorks and then use the SolidWorks to Anybody plugin to import your machine's design into Anybody and then run man-machine simulations. So you can get some both good-looking as well as fairly realistic models for your simulation. So on that note, I will wrap up and just introduce you to this demo, which we'll be doing right now. It's a very simple ergonomics problem. A person trying to lift a box up, and we're trying to predict everything. There's no motion capture data. We're trying to predict all the ground reaction forces and all contact forces. And we also have a simple exoskeleton. So on this note, I will give the word over to Casper right now, just so that I have a few minutes to try and set up or ready myself for the demo. And I will be back with you very soon.
All right, thank you, Anand. Very interesting. While Anand is quickly switching his laptop, I would like to remind you that you are still very welcome to give us some questions, both regarding the presentation you just watched and also the live demo that Anand is gonna do right now.
Great, thank you for that, Casper. And I think you guys, so you are seeing my screen right now. And so what you see is the folder containing all the files that we will need today in order to create our model. But let me bring your attention to this one file over here, demo_main.ne, because that is the only one that we will be modifying during this demo. The .ne extension stands for AnyScript, which is the programming language for the Anybody modeling system. So I'll go ahead and open this file in the Anybody modeling system. And as you see right now, it looks fairly empty. And this is because we've, in order to make this demo rather intuitive and also interesting, we've tried and we've essentially prepared chunks of code that have been tucked away in individual files. And the code in each of these files performs a very specific function. So we will be including those files in a certain sequence, and we will then be seeing what effects those files have on our model. Even though this is an empty model, I can still load it. And just some preliminaries, just to make sure that you enjoy the rest of this demo. I would like to bring your attention to the left of the screen, where you can see this big yellow blob. And if I switch over to the model tab, you can now see that there is a folder with the name main, and then there are two subfolders with the name model and study. Now, if I turn your attention back to the AnyScript window, you can see that you see the same structure. You see model typed within the main folder, and this is essentially how the model tree on the left and the AnyScript window are actually related. And this is how a model is. Yeah, so basically, an Anybody model is just a set of file folders and subfolders. So with regards to the study, I would like to again bring your attention to the left of your screen, where I will now switch over to the Operations tab, and I can expand the study folder over here, and you will see that there are different kinds of analyses that you can run with your model. Initial conditions is just for initially assembling your model and satisfying all the constraints, and then you have a kinematics study which resolves all your drivers and imparts some kind of movement, and then you have your inverse dynamics study, which of course, as we discussed, runs direct muscle recruitment. So we will now go ahead and start off with making our first set of changes to the model, and this would be to import the human model from the Anybody Managed Model repository. So this is done over here. This is the line that I just included, and you can see that there is a hash include statement followed by a file name, and if I were to double click on the file name, it opens up the file, and you can see that this is the code that has been tucked away over here, and its function is to just load the model. And for those of you who would like to download this model and have a look for it yourself and even request for a trial and probably try it out on the Anybody modeling system if you do not have it already, then Casper will tell you how to get it. And I would recommend that you follow all this green text, which is just comments and summaries of what exactly is going on, which should help you with getting an understanding of what's going on with the code. So now, having included that line, I'm going to load the model, and I'm going to switch over to the model view, where you can see now that the model has been loaded. This is a three-dimensional model. So at this point, there really isn't any motion that has been given. The model is just hanging out there in space. So we will go ahead and make some more changes now. So we did speak about the man-machine model consisting of course, a man component and a machine component. And the next two lines of code that I will be adding will essentially just initialize two folders to hold the man and machine components of the model. So if I reload the model now, the model view will not look any different. But if I turn your attention to the model tree, which is on the left of your screen up here, you can see that the model folder now has two subfolders, which is man model and machine model. Now, I think from now on the pace will pick up because I think you would be getting the idea of what to look for where. So the next step is to define a preferred posture for our model. Now, you might have seen from that figure, that last figure that I showed in my presentation, that the model is that of a person standing up and holding a. So we are going to define a preferred posture that the model would like to assume when it's holding this. And we do that by the code in this particular file, which essentially defines a preferred posture. And it does this by means of, it defines a set of soft drivers, which set the value of each degree of freedom, such that the overall posture of the human model resembles normal casual standing. However, given that these are soft drivers, you would recollect that these will always lose out to hard drivers, whose constraints will be given more preference if they cannot be met. So I will then go ahead and add to this. I'm still not going to reload the model because there's nothing interesting happening yet. But I'm now going to go ahead and insert a force plate that will be capable of predicting the ground reaction forces. Now, this is exactly the class of force plates that we discussed in the presentation. And I'm also going to actually, I'll probably just reload the model at this stage, and we'll take a look at what exactly has happened. So if I were to switch over to the model view, you can now see that at the base of the human model, there is this gray circular disk that has appeared. And this gray disk is the force plate. And in fact, there are two of them, one for each foot. But the reason why they're completely overlapped is because we've just loaded the force plate. We haven't really defined its orientation with respect to the model. So we will do that by including the next file, which will use a set of hard drivers to connect the feet of the model to the force plate. So now if I were to reload the model after including this last file, and if I switch over to the model view, so I'm going to go to the operations tab again that will appear on the left. I'm still in the model tab. I've just switched to the operations, and if I run initial conditions, it makes sure that all the required constraints are satisfied. And you can now see that the force plates have snapped onto the feet of the model. So now we sort of have a basic framework ready, and now we need to sort of put the model in a posture that we like to simulate. Now there is no way of controlling this model as it stands right now. So for this, we will add a set of tools known as widgets. A widget is a tool by which a user can actually interact with the model through the model view window that you're seeing right now, and actually sort of play around with the posture of the model. So what we will do is we will add two widgets over here. And these widgets are used for positioning the foot in space, and they include hard drivers. So which means if I drag the widget to a certain point, a hard driver will ensure that my foot follows it. So I'm going to load the model again. And if I were to run initial conditions and probably zoom in a little bit, zoom in close to the feet, you can now see that each force plate has its own reference frame with these small yellow boxes at the very end of those reference frames. And so these are the widgets that I can now hold and drag to position the foot. But each widget is also linked to the inverse dynamics study, which means that if I drag any of these widgets, inverse dynamics will automatically be run. So I'm going to get a hold of the widget on the left leg and drag it slightly in an upward direction. So you can see that the model has immediately repositioned itself and made sure that the foot has followed the widget, but then the rest of the model has taken up a rather weird posture. And this is because of a wrestling match that is going on between the hard drivers, which define the foot position, and the soft drivers, which we define for the standing posture. So the hard drivers are obviously satisfied, but then the model is trying to put itself in a posture where it thinks it is very close to normal standing. Although we as intelligent humans and not a computer can see that this is very far from the case. Another thing that I would like to draw your attention to is at the bottom of the screen. So you can see that there is a message window which seems to have given us an error with inverse dynamics. So what could the reason have been? If I rotate this model slightly, you can see that right now we had a set of hard drivers and soft drivers which wrestled and put the model in a certain position. But now this wrestling, as a consequence of this match, of this wrestling match, the model is now leaning backward in a rather unnatural position. So which means the force prediction algorithm cannot produce any physically feasible forces, ground reaction forces, that can actually equilibrate the model in this pose. So now we need to introduce some notion of balance into this model. So we do that by using a set of hard drivers. So we've defined, so this file that I include over here, called balance drivers, essentially first creates a set of measures for the center of mass of the human body, and then uses drivers to make sure that the center of mass always lies at the midpoint between the 2 feet as projected onto the horizontal plane. So I'm now going to reload the model, and I'm going to switch back to the model view. So the model is reloaded. I can now run initial conditions. And now you can see that the model is actually leaning slightly forward, and that is because now because I've run initial conditions, the center of mass constraint is already in place and it's trying to balance. Now if I were to do exactly the same thing that I did with the widget the last time, which is drag it slightly in the vertical direction, you can see that the model now has a much more realistic pose because it's balancing. And inverse dynamics has now succeeded. So if you look towards the feet, you see these two red arrows that are pointing from the force plate, and these are the predicted ground reaction force vectors. So at this stage, the lower half of our model seems fairly stable. We have a good ground contact model. So we'll go ahead and insert the box for our to continue our ergonomics model. So for this, there is going to be one file which inserts the box. And then I'm going to insert a contact model between the hands and the box, and this will be a predictive contact model as well. If you think about it, the ground reaction force prediction force plates are in theory capable of predicting any kind of, or simulating any kind of friction-based contact. So I'm going to use exactly the same class of force plates, but just on the hands this time, to model the contact forces between the box and the hand. Before we load the model, I will go ahead and also introduce a set of hard drivers, which will be included in this file, which will connect the model's hands to the box. So if I were to reload the model and switch over to the model view and do the usual grind, now try and run initial conditions again. So things are going to look rather messy this time. Let's also run inverse dynamics, and let me hide all the muscles so that we can see what is going on here. So inverse dynamics should be succeeding anytime now. There it goes. So you obviously have the ground reaction forces in the foot that have been predicted, which you can see right here. And if I move it slightly upwards, you can now see that it also has a predicted ground reaction force for the hands, and the hands have been locked onto either side of the box as well. However, we aren't, no one's going to hold the box this way. It's quite cumbersome. So we will go ahead and now add a widget to the model for positioning the box. Now this widget is also a hard driver. So this widget, so all the hard drivers that we are adding right now for the widgets will always be given preference over the constraints that are being specified for maintaining the standing posture. So this is one way of sort of trying to get a trade-off between between a natural posture, sort of trying to get the closest posture towards a natural posture. So now I can run my initial condition analysis, and you can now see that the box has taken on, sorry for that. Just need to rotate the model a little bit. And you can now see that the box has taken on a much more realistic position relative to the body. Now at this stage, I can move the widget slightly, just so that you can see just to coax it to run inverse dynamics. This is another way, instead of going and clicking on the inverse dynamics study. And yep, so inverse dynamics has succeeded. But what we see over here is we see that the muscles of the arms have now changed color. This is because, so the more pink a muscle is, it means the more it is being activated. And we believe that this high activation is now being caused by the box itself, which is pretty heavy. It's 10 kilograms. And you can see that just the way the person is holding it at the moment, just because of the way we position the widget and also the balance constraints, the box is, it has pretty large moment arms with respect to the joints of the arm. Additionally, the model also has to try to squeeze the box as hard as possible so that it can generate normal forces that are high enough to generate large enough friction forces to hold the box up. So given this scenario, we are now going to try and ease some of the load of the right arm by inserting an exoskeleton. Before I do that, I'm going to include a quick step over here, which I won't really go into a lot of explanation of. So this is just because we're adding a lot of widgets to the system, each of which is a hard driver. And to prevent these hard drivers from fighting with each other, I've just added a code which just ensures kinematic robustness. So next, we're going to add two files at the same time. So as you see, the first file inserts an exoskeleton in the model, and the second file connects the exoskeleton to the model. So it makes sure that the elbow joint of the exoskeleton is exactly aligned with the elbow joint of the model. So this is done using, again, a set of drivers between the arms and the exoskeleton. So if I now run initial conditions, you can now see that the exoskeleton has automatically been assembled on the arm with the help of the hard drivers. So now if I were to pull the box slightly outward in pretty much the same fashion that I did last time, you will see that once inverse dynamics is finished off, there is going to be a differential load on the right and the left arms. But wait, that did not happen. And the reason was because we just loaded the exoskeleton at this stage is just like an arm brace. We haven't really specified how this exoskeleton has to cooperate with the human body in order to produce a lifting action. So what we do is we need to explicitly convert the exoskeleton into an actuated exoskeleton, and make sure that this exoskeleton is included in the cost function. So that will be done by this file. And as a second step, and before I reload the model and run it again, I'm going to include some additional drivers. And I'll tell you why I'm including these drivers. If you look at the model view, you can see that the back seems to be arched rather unnaturally. And at the same time, the shoulders are somewhat shrugged or they are raised upward when it's trying to hold the box up. So in order to try and get the model to look a lot more relaxed and to coax it to use more of its elbow, to bend its elbow instead of shrugging its shoulders, we're going to go ahead and introduce a few additional drivers. So at this stage, we've introduced the exoskeleton and the additional drivers. So these are the most recent changes we've made. And we should be almost coming towards the end of the demo now. This is probably the last simulation-based step. I'll show you some interesting visualization tools that you could use beyond that. So if I were to do initial conditions and then again pull this widget out slightly, you can now see that the model has a much more relaxed pose of its back and its shoulders, and the elbow is a little more bent than it was the last time. And now we should be, oops, I think I forgot to pull the widget. And so you have inverse dynamics running over there. It seems to be taking its own sweet time. Yep. So now you can see that the muscles of the left arm seem to be pink, just as loaded as they were earlier, while the muscles in the right arm seem to have gotten rid of a lot of the load thanks to the presence of the exoskeleton. Now for our final addition to the model, I'm going to include some tools for visualization. So over here, let me walk you through what these three files do. So this first file, which I've just highlighted, helps you visualize the glenohumeral contact force, that is your shoulder joint. It helps you visualize that as a vector. The second tool helps you, sorry about that. Yeah, the second tool helps you color your exoskeleton according to the amount of torque that it is producing. Your third tool helps you insert a spiraling camera into your system, and so this will help you record views of your model. And if I were to now switch over to model view, run initial conditions, and I'm going to run inverse dynamics right now. I'm not going to touch the widget because right now the model is in a symmetric position, and I don't want to disturb that symmetry, because we're going to visualize the contact forces in the right and left shoulder and try to see whether the exoskeleton has had any kind of effect on those forces. So this is the perfect front view, and you can see that. So this is the sort of the complex or the rather unintuitive functionings of the musculoskeletal model is that you can see over here, because you had an exoskeleton on the elbow, which can clearly affect your shoulder joint reaction forces in some way. So the shoulder reaction forces are actually slightly lower in the case of the right shoulder, and that is the arrow that you see pointing from the left towards the right. And the other vector that you see over here is your left shoulder reaction force. So you can see that the exoskeleton surely has helped the shoulder as well in some way. And if you wanted to quantify these observations, you could obviously go into the model tree and try to retrieve the actual values or the magnitudes of these two forces. And similarly, you can see that the exoskeleton has now some form of, it's mildly colored. The more red it is, the more torque it is producing. And if I were to try and bring the model, the box closer to the human body, we would expect the joint moments to reduce. And if you keep looking at the exoskeleton, the color should actually change slightly, and it should go slightly lighter, which you see right now. So on that note, I'll just leave you with, we also inserted a camera, but then running the camera can be boring running the camera simulation can be boring for a viewer. So I've already created a video file, which is the output of the camera. And what you see is just, I'm not sure of how badly this video is framing on your computers, but yeah, it is basically a camera that is spiraling around, and you basically see you record a smooth video of the person from all around. Great. So on that note, I would like to transfer the word back to Casper, who will now go into the question and answer session.
Yep. So if you think that you would be interested in using anybody for your research, and if you want to try out the model from today's webcast, you can go to our wiki page and you can actually download it already now. So this is our wiki page. It's wiki.anyscript.org, and if you go down to model and validation, there will be a link down here called example from the man-machine webcast, and if you click that, you're directed to a page where you can download the exact model that Anand has just been showing. And if you do not have the Anybody system yet, I would like to remind you that you can always request a trial license for 30 days by clicking our license link on the front page and inquire a license. Yeah, so please do that if you're interested. The next webcast is on April the 20th, and it's called Personalize Your Musculoskeletal Models Using Medical Image Data. So this will also be an in-house webcast, and it's gonna be a kind of hands-on scaling webcast. Then I would also like to mention our YouTube channel. You can search for Anybody Technology and see all of our previous webcasts in there. Then there's of course our webpage where you can check out events, dates, our publication lists, and so on. And the InnoScript forum, of course, where we answer questions, and the wiki that I just mentioned. The events that we would like to tell you about is mainly ESB 2016. So at ESB you can come visit us at our booth, and at the ESB we will also be doing a free workshop at the Crown Plaza Lyon Hotel. It's 5 minutes from the ESB venue, and it's on the 10th. And registration, so please reserve the dates for when we open the registration. So now it's time for our questions.
We hear Casper?
And Anand is ready. So our first question is for these driven motions.
Mm-hmm.
If it's possible to input some accelerations patterns as a constraint for the model or for the joint movements.
Well, of course it is indeed possible. So there is actually a driver which is a constant acceleration driver. So you could either set that to a joint, or it could even be, so in the example that we saw, let's take the example of the leg press machine, which was one of the examples which we saw for machine-driven motion. So you could actually, so the foot plate of the leg press machine is what actually moves, and you could specify the acceleration of that particular plate, or if you directly wanted to specify the acceleration of a joint, you could simply, so the model comes with certain inbuilt kinematic measures to measure the joint angle, and you can go ahead and give it the same driver for acceleration driven motion.
Awesome. Then there's a question regarding the exoskeleton, whether the torque was applied from the joint, elbow joint, or if it was applied at the bicep and wrist.
Got it. So the torque was actually applied as a torque on the exoskeleton's elbow joint. This torque was then transmitted through to the body by means of the reaction forces. However, in this particular model, just to keep things simple, I haven't used special contact elements. But in reality, what you could do is essentially just use a set of what we talked about with regards to special force elements was decouple kinematic constraints from the kinetics needed to maintain that constraint. So you could use a set of kinematic or kinematic drivers to try and position the could maintain those constraints using reaction forces that were actually applied at the forearm and the upper arm. But yeah, but you could still the torque applied by the exoskeleton would still be transmitted to the human model by means of these special force elements.
Okay. There's a viewer questioning the back muscles, why they aren't activated when the model is lifting the box.
Okay, actually the back muscles are activated, and it's my bad that I did not spin the model around all the way and actually show you what's happening. But the reason why we saw very pink muscles in the arm was because those muscles were getting very close to being completely saturated. And that is the reason why this was just a warning sign. So the muscles at the back might not have necessarily been activated to the same extent. But again, I should have spun the model around and shown it to you.
So we are running late right now. So I think that was the last question for tonight. So thank you all for listening in, and have a afternoon or a good night. Goodbye.